Hello and welcome to Controllerstech. This is the 8th video in the STM32 UART series, and today we will start a mini-series on the Lin bus. The Lin stands for Local Interconnect Network, and just like the Lin Protocol, it is also majorly used in the automation industry. Compared to the Lin Protocol, it offers lower performance, speed, and reliability, but it reduces the cost drastically. I have made a separate playlist for the Lin Protocol, and the first video in the playlist explains what this protocol is, and where and why it is used. Do watch this video if you don't know what the Lin Protocol is. Today in this video we will program our STM32 MCU as the Lin master. I am not going to connect any transceiver in today's video, we will simply see how to send the data in the protocol format. In the next tutorial, we will connect an actual Lin transceiver and receive the data using another slave. So today we will just focus on the protocol formatting. The Lin protocol uses the UART peripheral to transmit the data, so we need to arrange the data in a proper format, so that it is recognized as a proper Lin data. I am going to focus on the Lin version 2.1, as it is the most recent one. Here I have the Lin Specification package for the version 2.1. We will just see some important things in this specification package. Here on page number 28, you can see a typical Lin frame. A Lin frame consists of a header and the response. The header further has the break field, sync field, and the protected identifier field. The response field consists of the data bytes, which can be up to 8 bytes, and the checksum byte. We will basically program our MCU to send this frame, and then read it on the logic analyzer. Let's start the Cube IDE, and create a new project. I am using the STM32F446RE. Let's give some name to the project and click Finish. I will start with the clock setup first. The MCU will use the crystal from the ST-Link, so bypass it here. The board has 8 MHz crystal on it, and let's run the system at maximum 180 MHz. I am going to use the UART1, so let's enable the UART1 in the Lin mode. The pin PA9 is the UART TX pin, and PA10 is the RX pin. Note that Lin is a single wire protocol, but we still have 2 pins for the UART. This is because we can't use the MCU directly to the Lin bus, instead we would need to use some transceiver in the middle. The Lin bus used in cars generally uses the 12-volt signals, hence the use of a transceiver is necessary. I will connect a Lin transceiver in the next tutorial, but today we will just focus on the TX pin. The data sent by the MCU will be via this pin, so we will monitor this pin on the analyzer. The Lin protocol uses the baud rate of up to 20 kilobits per second, but I am using the baud rate of 9600 here. The word length is 8 bits with 1 stop bit and no parity. The break detect length is the length of the break field, which is set to 10 bits. This is used in transmitting as well as in the reception. That is all the configuration we need for now. Click Save to generate the project. Let's define a TX buffer where we will store the data to be sent. The break will be sent by the UART peripheral itself, so we will send the sync field first. The sync field consists of the fixed value 55 hex. After sending the sync field, we need to send the protected ID. The protected ID consists of the 6 bits ID followed by the 2 parity bits. Here you can see the table containing the protected IDs, for the equivalent ID fields. For example, if the ID is 0, the equivalent protected ID will be 80 hex. And if the ID is 19, the protected ID will be D3 hex. You can directly use this table to find the required protected ID for the equivalent ID field, but I will write a code to convert the ID to the protected ID. As I mentioned, the protected ID consists of the 6 bits ID, along with the 2 parity bits. Since we have only 6 bits for the ID, the maximum value of the ID allowed is 63, or 3F hex. Now to find the parity bit P0, we have to perform the Exor operation between the ID bits 0, 1, 2, and 4. And to calculate the parity bit P1, we have to first perform the Exor operation between the ID bits 1, 3, 4, and 5, and then negate the value obtained. Let's write the code to do this. The function PIDCalc will take the actual ID as the parameter. The maximum allowed ID is 3F hex, so if the ID is greater than this, we will call the error handler. Let's first extract each bit from the 6-bit ID field, and store them in the ID buffer. Now to calculate the parity bit P0, we will XOR the ID bits 0, 1, 2, and 4. Similarly, to obtain the parity bit P1, first XOR the ID bits 1, 3, 4, and 5, and then negate the obtained value. Now let's store the parity bits along with the ID bits, and store them in the ID variable. The ID is now converted to protected ID. Finally, we will return the obtained protected ID. Now, as per the Lin frame, after sending the sync field, we need to send the protected ID. So let's store the protected ID at the next position in the TX buffer. Here I am using the ID 34 hex, which will be converted to the protected ID, and will be stored in the TX buffer. Next we will send the data. The data can be up to 8 bytes, so I am going to send all 8 bytes. Here I am storing the data at the very next position in the buffer. At the end we have the checksum. The process of calculating the checksum is given in the appendix. Basically we have to keep adding the data bytes. If the result is higher than 255, we will subtract 255 from it. The checksum calculation varies as per the Lin version you are using. For Lin 1.3, we use the normal checksum, where we only perform the addition operation between the data bytes. But for Lin 2.1, we use the enhanced checksum, where we perform the addition between the data bytes, as well as the protected ID also. Let's write a function to calculate the checksum. The parameters of this function will be the protected ID, the pointer to the data array, and the size of the data. Here we will first combine the data bytes and the protected ID in a single buffer. So let's copy the protected ID to the first position in the buffer, and the data to the next position. Now we have all the required data in the buffer array itself, so let's add the data. We will keep performing the addition, and if the sum is greater than 255, we will subtract 255 from the sum. The output of this loop will be a value less than or equal to 255. In the end we need to invert the result, so subtract the sum from 255. This is also as per the instruction given in the specification manual. Let's go back to our TX data buffer. We have the sync field, the PID field, and the 8 bytes of the data. Now we will add the checksum to the last byte of this TX buffer. The PID is already stored in the TX data 1, so let's pass it here. The actual data starts from the offset of 2 in the TX data buffer, and the data size is 8 bytes. As I mentioned, the Lin version 1.3 does not use the PID for the checksum calculations, so if you are using version 1.3, you can pass 0 to the PID parameter. Now we have the complete data to be transmitted via the Lin bus, so let's start the sending process. We will first send the break field, so call the whole Lin send break function. Then transmit the TX data buffer. Let's give a delay of 1 second, so that we can observe it in the analyzer. Alright, let's build and flash the code to the board. Here you can see the pin PA9, the TX pin of the UART1, is connected to the logic analyzer. We just need to check the data sent by the MCU, so this much connection is enough. Let's open the analyzer software. Let me change the baud rate to 9600. I am also adding the Lin analyzer to the same channel, and set the baud rate to 9600. Alright, here you can see we are receiving frames every 1 second. Let's analyze one of these. Here the frame starts with the break field, which was sent by the function Lin send break. Then we have the sync field with the value 55 hex. Then we have the protected ID B4 hex, but this is recognized by the Lin Protocol as the ID 34 hex. This is the actual ID we sent, and if you check the appendix, the PID for 34 hex is B4 hex. This is the PID transmitted by the MCU. Then we have the 8 bytes of the data field. And in the end we have the checksum. The checksum is 2F hex, and this is correct. I am saying this because if the checksum is wrong, the Lin protocol will identify it as the wrong checksum. Let me demonstrate this. I am commenting out the part where we calculate the checksum, and instead I will send another random value here. Let's see how the analyzer reads this. You can see we have the entire frame as it is, and the checksum is 3F. The Lin protocol recognizes this as the wrong checksum value for the data sent previously. This means that the checksum we calculated was correct. So we are able to transmit the data in the Lin protocol format. The analyzer can decode this data pretty well, and hence verifies this as a valid Lin frame. In the next video we will connect an actual transceiver module to our MCU. The transceiver will convert the received data to the Lin voltage and transmit it over the Lin bus. We will also use another transceiver to convert the data back to the TTL format, and then read the data on another MCU, the slave. This is it for today. I hope you understood how to get started with the Lin protocol. You can download the code from the link in the description. Leave comments in case of any doubt. Keep watching, and have a nice day ahead.